Good morning, everyone. I welcome you all to ET Energy World webinar. To present this webinar, I welcome Mr. Deepak Krishnan, Associate Director, Energy Program, WRI India, and share valuable insights on the topic Parched Power, Water Demands, Risks and Opportunities for India's Power Sector. There will be a presentation on the topic followed by a question and answer session wherein you may submit text questions to today's presenter by typing your questions into the questions pane of the control panel. You may send in your questions at any time during the presentation. We will collect those and address them during the question and answer session at the end of the presentation. Now I request Mr. Deepak Krishnan to start the presentation. Over to you.
Thank you very much. First up, good afternoon, everyone, and thanks for taking time out to join this webinar. Thanks to ET Energy for giving me this opportunity to present this work to a larger audience. I look forward to sharing with you some of the key findings from this study, and more than eagerly, I'm looking forward to seeing what questions or suggestions that you may have for us. Very quickly, a brief about WRI for those of you who don't know us. We are a global research organization and we are present across these geographies, as you can see on the screen. And we work across these areas, particularly climate change, energy, water, which are of importance and particularly relevant to today's webinar. First up, I would like to start off with the building blocks of this presentation. So these are the three research papers on which this webinar is built upon. I am happy to share these with you if you're not able to find them online. They are available, the bottom two, that is the methodology and the main Parched Power paper are available on the WRI site, and the other one is there on IRENA's website. But in case you are not able to find these, you can contact me. I'll share my email at the end of the exercise. So coming in particular to the methodology underlying this study, when we started to evaluate what is the water stress for the Indian power sector, that is to see how much water the power plants are using, both from a withdrawal and a consumption perspective. What we found is that unlike information about electricity generated, coal stock at power plants, this kind of systematic collated information on a monthly or an annual timeline was not available anywhere. So much so that even the water statistics for the country, which talk about what is the demand and the supply, were last done by the Central Water Commission in 2015. It was only in June this year that Niti Aayog came out with their water management index. I'll touch upon that a little later in the presentation as well. So this got us thinking as to see how we could actually access this information. We knew that some of the companies who operate these power plants have their sustainability reporting mechanisms in place by which they are able to definitely capture this information. But a large majority of plants do not have this information out in public domain. Again, we are sure that they would be tracking these, measuring these, but the key thing was having this out into the public domain, because it is water, as you know, is a social good, and it's important. It's used across sectors. So that's when my colleagues came up with this methodology of using satellite images of power plants and a machine learning algorithm. So the simple technique is this. So using satellite images, we capture the photos of a power plant. From that, we are able to understand what is the cooling technology that is used in that power plant, and what is the fuel type of that power plant. These are then correlated to the withdrawal and consumption factors. That is to say, how much water is withdrawn or consumed per megawatt hour of electricity generated from that power plant. And using this information, which is available in literature, and we also have customized values for the Indian power sector. So using that, we were also able to then multiply it with the net generation from the power plant, which would give us the total estimated water withdrawal or consumption numbers. So once this analysis was done, we then compared it back with the information available with the Energy Information Administration of the US, where this information is available on a more systematic basis. And based on that, we were able to obtain a high degree of accuracy, which gave us the confidence to continue with this method for Indian power plants. Now, satellite imagery-based analysis is very powerful, and this is just one of the many applications in the power sector. Yesterday, for instance, there was a report that came out which talked about which shows how to estimate the plant utilization factor of the plant using the image of the smoke plumes that are coming out from the power plant. So there are interesting applications, and this is just one of them. So how does a brief, I'll just take you through briefly about how this system works. So for instance, if you see the two example images that I have put in, these are characteristic images of a once-through system and of a dry cooling system. So in a dry cooling system, as you can see, there are these accordion type structures which are present, and that more or less correlates to a dry cooling system. Whereas if you see a once-through system, you see the distinct intake and the outlet. So similarly, each of the plants has this characteristic feature, one or more characteristics features, which we use to train the machine learning algorithm. And as far as fuel type is concerned, a similar approach based on imagery. For instance, if you see a coal power plant, the distinct coal pit. Similarly, in gas plants, you would have that dome-like structure. Similarly, same dome-like structure in nuclear power plants. Biomass pit, the distinct color difference from that of a coal power plant. So these are distinguishing factors which are then used to feed information and train this algorithm. And as I mentioned earlier, we ran this information against plants whose information is already put out in the public domain and able to correlate the results. Now, these are the data sources that we have used in the study. Largely publicly available data. One is definitely, a lot of you will be familiar with this, the plant and regional level daily generation data, the capacity data, what is the unit level rate of sale, what is the daily outage data, and this is going to form a crucial part of this study and to a lot of the implications. And I was also talking about the country-specific water withdrawal and consumption factors. So this on the rightmost column, you can find the authors of the study, which customize these values for an Indian situation. We also leveraged a tool that we have called Aqueduct, which measures the water stress across different regions, both in the present and also provides future estimates. And then we were able to overlay the two and conduct this study. So to start off with, water by itself isn't the number one issue today. As far as power plant outages are concerned, they aren't number one, as is evident from this graphic that I have put up. While you have the planned outages, which are always factored in, even among the forced outages, it ranks number 5. And even if you see the scale of how many units of electricity have been affected by water shortage vis-a-vis the equipment failures, you will definitely find that the equipment failures dominate significantly. And interestingly, this data which we looked at from 2013 to 2016, if this itself is showing you a situation where water isn't the number one cause, after the release of the study, what we found is that the situation as far as water shortage is concerned is has actually improved in the sense that not as many plants faced an outage situation as with respect to water. In fact, only one unit of Chandrapur is consistently out because of lack of water, as per the latest CEA information available. Fine. As on today, it may not be a problem, but in future, please. This is a graphic from Niti Aayog's CWMI. And as you can see that while in 2008, we were more or little comfortable as far as demand supply situation is concerned. When it goes to 2030, you're definitely going to see a near doubling of the gap between the demand and the supply. And this is a serious constraint because it's not just our sector which is going to depend upon water. There is agriculture, which is a mainstay, and it's a daily need for all of us. Similarly, you have a growing urbanization of the country, and that also is something where people will need water for their daily uses. And with this in the background, we have also seen the situation of Cape Town, the day zero situation coming in. Also, a lot of cities, particularly Bangalore, people are projecting that groundwater is going to run out by 2030. Niti Aayog study itself saying that 6% of our GDP will be lost by 2050 if we continue on a business as usual. So keeping all this in mind and the fact that we always need to be prepared for the worst in the future, there are certain steps which we can take as far as the power sector is concerned when it comes to conserving water and utilizing it judiciously, and we'll touch upon some of those going forward. But as we have seen earlier, power plants do shut down due to water shortages. And this iconic picture which BBC had taken is of the Farakka thermal power plant in West Bengal. And this was, I think, in 2015 or 16 at one of the worst situations that had seen. The key messages is that India's demand for water will grow, and we are a water-stressed nation. In fact, if you see maps of water availability and water stress, you'll find significantly deep red marks on the Indian map, and I have a slide on that as well going forward. And 90% of our thermal power generation depends on fresh water for cooling. Now, a key thing is that water shortage itself is something which has to be qualified. For instance, this is from a plant's perspective. That is, the plant did not get water for its operation. But post the study, we have been doing a bit of ground truthing with some generators and find that while the CEA statistics mark these kind of situations or water shortages, it is not necessarily that there was a drought or lack of a failure of the monsoon in that particular region. There were plants which had a situation where water which was originally assigned to them had been diverted because a road or a barrage had to be constructed, and in that particular period they didn't get water. There was another plant where the intake system was filled with silt, and therefore they couldn't join water. Farakka itself, what we understand is that the intake system had been designed before the India-Bangladesh treaty had been signed. So once the water allocation to Bangladesh took place, the natural gravity flow didn't happen in these channels. So while the point I wish to make through this is that while the satellite studies do provide some initial overview, they by themselves are not conclusive and definitive. One also needs to do a bit of ground truthing to actually verify what exactly contributed to the shutdown. What it means, for instance, if you see between 2011 and 2016, our thermal utility generation grew by 40%. But for the thermal sector as a whole, if you see the latter two graphs, especially I would like to request your attention to the rightmost graph, wherein the fresh water withdrawal has stayed relatively stable between 2011 and 2016, whereas the freshwater consumption has increased by 43% in the same time period. We believe that this is due to changing cooling technology, which is being used by thermal plants. So instead of a once-through system, increasingly recirculating systems are increasing. But our view is that this results in increased consumption, which means there is less water for the other sectors. At this point, there is also one thing which the audience needs to note is that this study only talks about the quantity of water that is either withdrawn or consumed. At the same time, it is also important to recognize that water quality is also an important parameter, and by quality, I mean what things can get mixed into the outlet, what is the temperature of the outgoing water. So those are things which we have not covered as part of this study. So it is only purely a quantitative study. So from that perspective, if you see increased consumption is there in this period, and we believe that is due to the change in the cooling technology mix. The important ramification of this is that if you see the new MOEF guidelines, there is a significant thrust on moving all the plants to recirculating technology. While at this stage we don't have a definitive answer on whether that is the right thing to do or not, but this is something which I feel needs to be kept in mind. That having recirculating technology increases the freshwater consumption in the plants mix. So overall, if you see, if you analyze all the forced outages, 61% of the time we found that the programmed thermal generation couldn't be delivered. So where it actually hurts us is that we, as a country, plan a lot to get these plants in motion, get them commissioned, overcome a lot of hurdles with respect to land acquisition, securing fuels, securing the power purchase agreement, only to see that a lot of our capacity addition is negated by some of these forced outages. Now, if you take water related outages themselves, more than 30 terawatt hour of generation was lost due to unavailability of water. And if you see the 2016 number alone, that it could have powered Sri Lanka for an entire year. That's a significantly large amount of generation to lose out on. And who knows, some of it, if it had been available, we could have moved faster on our electrification targets as well. And this is the graph that I was talking about, wherein we have mapped almost all the thermal power plants onto the water stress map of India. And almost 40% of our freshwater cooled thermal capacity is in high water stress areas. While I reiterate again that today, if you go by the earlier graph that I had shown, that water may not be a very, very, very major issue right now. In future, if you see that these stress maps also take into account other demand for that source of water, and keeping all that in mind, it is certainly a concerning picture to see. And high water stress plants, as it would be obvious that they have a lower average capacity factor compared to those in low and medium water stressed areas. But does that mean that low and medium water stressed area plants can relax? No, because as we have seen earlier, there are regions which are low and medium water stressed, but at the same time, plants located in or near those areas have also faced outages. And based on the further analysis on the water stress, what we tried to do was to categorize the plants into different regions and assess what would be the increased level of competition by 2030. And for that, we tried to take a look at what is the stress level that is likely to happen in 2030, what is the additional demand that is going to come in due to other sectors. And you can see that a large number of plants, it's only a lot of plants are more likely to face competition from other sectors like agriculture, municipalities, other industries, rather than a decreased level of water stress. And just to carry this analysis further, what we saw in our analysis that if you take the generating mix state-wise, there are some plants which are more freshwater efficient compared to others. Of course, Tamil Nadu and Gujarat are the outliers here, given that they have a larger proportion of sea-cooled thermal plants compared to other states. Whereas if you see at the rightmost end, it's Rajasthan, UP, Karnataka, and West Bengal, where the generating systems are dominated with a larger share of once-through cooling system, which means that their freshwater withdrawal intensity is higher compared to Telangana or Andhra Pradesh. What we also did was to take a look at different companies and see what is their freshwater efficiency and water stress compared to others. Of course, there are some good performers here like Tata Group, the Adanis and the GMR. There are some middling agencies. Of course, one also needs to keep in mind that the legacy of the assets that these companies may have under their ownership all contribute to this. So this shouldn't be taken as any kind of it's just to put all the companies into perspective and see where one can improve and what steps can be taken to improve. Now, staying on with the companies, what we also did was to take a look at about 20 companies out of the entire set. And we found that applying the same analysis on a number of hours of generation that was lost and the average selling rate from that particular power plant, close to $1.4 billion of potential loss was something we estimated. And that is a particularly large number. And given that recent instances of stressed asset resolutions are going on, while again, today, as on today, the water-related stress may not contribute a lot. Going forward, we feel that it would also play a major role. And also with a lot of investors, becoming more climate aware, insisting on more and more environmentally benign solutions and assets as part of their ownership. We definitely feel that this will also start playing a significant role in their considerations. What we then also did along with IRENA, while the previous set of slides only talk about particular plants and showed a methodology of how we could use to estimate, what we did along with IRENA was to take a look at the projections that are made by different agencies. IRENA themselves, CEA came out with their projections around a year and a half back. And we evaluated it based on 2 or 3 parameters. One is if the MOEF guidelines, which talk about existing plants changing to recirculating and limiting their consumption to a particular level, or renewables, India being able to achieve its renewable energy targets. So with all this in mind, what would be the impact on the sector's water withdrawal intensity and consumption intensity as well? So as you can see from the graph, clearly there is a significant gain as far as the withdrawals are concerned. And if you can see the 2 IRENA scenarios, there is a significant, much greater drop in the withdrawal intensity, mainly because the IRENA scenarios are very, very aggressive on renewables as far as the CEA scenarios are concerned. But even if you take a look at the CEA scenarios, the reduction is quite considerable. Whereas when you come to consumption, you'll find that the drops are not as high as what you see in withdrawals. So there is a reason to it also. For instance, if you see this particular graph, you find that the blue component in each bar chart, that is the improvement in the reduction in withdrawal because of the cooling technology improvement. So as far as withdrawals are concerned, the changeover to this new technique of recirculating cooling, not necessarily new, but to recirculating actually helps in significantly reducing the withdrawal intensity. Of course, with when you talk about the power mix shift, that is the movement to the renewables. Again, it's clear given how much lesser solar and wind plants consume, that will definitely contribute to reduction in withdrawal. And the plant efficiency, that is the more electricity you are able to generate for a given amount of water, as that improves also, you will find this. Whereas when you come to the consumption intensity, you'll find that the blue portion of the graph is all now in the positives. So as you would have linked it back to the earlier graph which I showed you on the increase in the thermal capacity versus the cooling, the consumption and the withdrawal intensity. The recirculating technology actually increases the consumption of water in the so as the generation levels increase, there is an increase in the absolute consumption as well. So what do we say is the way forward given that all this information which you have all had a chance to process? One is the MOEF directive of 2015. We feel even though it may not be 100%, as far as consumption is concerned, it is something which is there, and the same directives also they're a part of the air pollution directives as well. So implementing them is something we would definitely recommend. But we also feel that accelerating the transition to renewables would be something which we should not lose sight of, because the absolute decrease in the consumption of water by the sector needs us to transition to renewables. And some of the key recommendations which we feel can be implemented is, one is, while the MOEF directive talks about bring down your specific consumption to so and so number, what is the existing number? That itself is not known. And as all of you might be familiar with the adage, what gets measured gets managed. So at the moment, if you don't have this information put out in public domain, how do we know which plant is complying, which plant is not? So this kind of monitoring and disclosure needs to be done. We also need to have a standardized reporting on water data. I mean, on the lines of PAT, I would even go so far as to say that have mandatory water audits, which would put this, and then put this information out into the public domain. Set benchmarks and develop guidelines. What we realized when we talked to some of the generators on ground is that the water audits are also not very standardized. Different auditors tend to report different parameters. The way they measure, what they measure, all that is not standardized. So this kind of standardization is required. And once these standardized numbers are available, we do have a sort of a good time series of data to analyze and work on. Maybe they could be used to incentivize a better performance. What I understand is that CEA has already written to the power plants to start collecting this data from August 2018. So hopefully this should go a long way in bringing up this framework. We also recommend a regular company and investor level analysis. People may already be doing it, but for those who are not, this is something which you need to take a look at. Evaluate your portfolio to see what are the different risks from a climate perspective. And within that, please do consider water-related stress also. Last but not the least, integrating energy and water planning is something that is absolutely essential. No longer can sectors operate in silos. And the need of the hour is for different agencies to sit down and consider all the resources that we have, and try to work more from a integrated resource planning perspective rather than on standalone analysis of the sectors and then try to match different numbers which we have. So these were the points that I wanted to put across to you. Now I'm happy to hear any questions and feedback if any. Thank you so much.
Yeah, thank you for that, Deepak. We have already received a couple of questions. So the first question goes, how do SPCBs, I mean state pollution control boards, monitor water consumption by thermal power plants? If in case a violation is found, how are penalties determined and levied? Thank you.
Okay, so to my understanding, I am not aware of the penalty mechanism that an SPCB levies, but from what I could gather from different people on ground is that this is more reliant on a self-reporting sort of methodology, wherein the plant has to fill their annual reports with the SPCBs, and in that they mention how much water they are withdrawing or consuming. But what I would like to stress upon is that while people may be submitting it to the SPCB, the need of the hour is to put it out in a public domain, and also to build the confidence and the trust of the public. Also have